Yeah, so this is a work done together with my collaborators, Nat and Shankar, and they're both at QIP, so you can find them later. So I'd like to motivate Floquet codes by starting with the surface code. So in reality, if we are going to do quantum computation with the surface code, this is not what it's going to look like. It's going to look rather like this. Because as soon as there are measurement errors, we have to do repetition code based on surface code, which naturally introduces time direction. Therefore, if we want to do quantum computation with topological stabilizer codes, we in fact naturally do quantum computation in space-time, not just in 2 dimensions. Therefore, Floquet codes should take advantage of this, and perhaps we can come up with clever ways to do quantum error correction in space-time. And the first code that has been proposed is the honeycomb code, which has another advantage, that it is a code that is perfectly tailored to work on topological architecture for quantum computing. Since the work by Hastings and Haah proposing the honeycomb code, there was a surge of interest in Floquet codes, and a lot of new generalizations have been proposed. The original approach was based on a subsystem code, where the checks measured in the honeycomb code form a subsystem code, and the entire operation of a Floquet code can be understood based on that. But since then, several other proposals have been put forward, such as our work, and also other approaches such as domain wall pumping that proposes an EM automorphism code, anion condensation approach, and measurement-based quantum computation reproducing the operation of the honeycomb code. So in our work, we show that some of the significant restrictions or the structures imposed in the honeycomb code are in fact not necessary if we want to design good Floquet codes. In particular, we don't need to start with a subsystem code, and we also don't need a periodic protocol. As a result, we propose several new codes. One of them is a CSS version of the honeycomb code. Then we also propose non-periodic codes, which we call dynamic tree codes. And we also do a 3D generalization to fractal Floquet code. All right, and also CSS honeycomb code has been independently discovered in an anion condensation paper, and the authors are here. So, here I walk through the protocol for the CSS honeycomb code, and that should be enough also to introduce the honeycomb code because it's not that different. So we work on a honeycomb lattice, which is 3-colorable, and it also introduces 3-colorability of the edges. As such, for example, red edges connect red plaquettes on the lattice, and we put this lattice on a torus. We perform 2-qubit measurements of Pauli operators, and in our first round, which is round number -3, which we'll understand why in a moment, we measure XX operators on red edges. In a subsequent round, we measure ZZ operators on green edges, but we also add a specific plaquette to the instantaneous stabilizer group. And the reason why we add it is because we measured these plaquettes in the previous round. The measurements of the previous round do not commute with the new measurements, therefore they have been randomized, but the plaquettes stay because they commute with the new checks. In the next round, we measure XX operators on blue edges, and we generate additional plaquettes. And in the next round, we measure red edges again, but we change the flavor again, and we generate more plaquettes. At this round, this is round number 0. At this round, we actually have generated a topological subspace. We actually end up in a topological subspace of a toric code. And this can be seen by considering these 2-body checks as the fusion checks that create an effective qubit from 2 qubits on each red edge. By placing these qubits on a superlattice, we obtain a triangular superlattice. And the plaquette operators in the instantaneous stabilizer group become the star and plaquette stabilizers of the effective toric code when they're expressed through effective Paulis of the effective qubits. And if we continue in this fashion, we measure red, then green, then blue edges, and we oscillate between X and Z flavored measurements. We keep going through realizations of the toric codes centered around different colored plaquettes without losing logical information. To see that we are conserving logical information, it is the easiest to follow the logical operators on the superlattice. If we express the logical operators on the superlattice, they would be operators that wind the electric or magnetic strings around the torus, and they are nicely expressed through the effective logicals on the effective qubits. And if we follow these operators through the protocol, we will see that an instance of each type of the logical will survive from round to round, which tells us that the logical information will be conserved in this code. Then finally, the error correction in a nutshell works this way. So first of all, the errors, we can correct the Z and X type errors independently. And moreover, it turns out that we only need to detect the edge where the error has occurred in order to be able to correct the error. Next, if we want to detect only the edge, assume an Z-type error occurred after a residue check, and we need to detect this red faulty edge. For this, we use two detectors, the green X detector and the blue X detector, which will tell us the space-time location of the edge where the error has occurred. The detector works the following way. For each plaquette, we actually infer its value twice during each period of the code operation. And if an error occurred between the two measurements, the value of the plaquette will have changed, and we will know that the error must have occurred on one of the edges belonging to the detector. Now, for this specific error, two detectors will light up and will give us an ambiguous space-time location of the error, and we'll be able to detect it and subsequently correct it using minimum weight perfect matching decoder. Next, to summarize the properties of the CSS honeycomb code, it's easier to do it in juxtaposition with the original honeycomb code by Hastings and Haah. Up to a constant depth unitary, it can be summarized as a set of checks that are RXX, GYY, and BlueZZ, as opposed to our protocol, which is RXX, GZZ, BXX, RZZ, GXX, and BZZ. So we also perform red, green, blue sequence of colors, but we switch between X and Z, so it's a CSS protocol. So the original honeycomb code dynamically generates logical qubits. It has period 3. It conserves logical information and realizes story code. It also performs EM automorphism every 3 rounds, which exchanges the electric and magnetic sectors of the corresponding anyon theory. And it has a threshold. Moreover, if we take all the checks of the code and these checks turn out to generate a subsystem code, the stabilizer group of the subsystem code consists of products of checks around plaquettes and also around homological and non-trivial cycles of the torus. When we perform Floquet sequence from this subsystem code, we actually measure all the stabilizers of the subsystem code but 2. Therefore, this gives us additional logical qubits that were not there in the subsystem code. The subsystem code on a torus defines 0 logical qubits, and the Floquet code defines 2 logical qubits. And another consequence of this being viewed from the framework of subsystem codes is that the plaquettes in the ISG are permanent. Okay, so in comparison, the CSS honeycomb code has similarly good properties, has a threshold, but it has period 6. The EM automorphism is only apparent if we also conjugate the code by onset Hadamard after every 3 rounds. And importantly, it doesn't have a representation through a subsystem code, because if we collect all the checks, we can formally write out a subsystem code, but the stabilizer of the subsystem code will be null. Moreover, if we try to play around with the definition of subsystem code and throw out, actually, this is not the latest version of so it has an error, we should throw these out, actually. Sorry about it. The slides will also miss some nice jokes that we inserted last moment. So also if we play around with the definition of the subsystem code, it will not help. We still cannot reconcile our construction with the concept of subsystem codes. As a consequence, none of the stabilizers in the ISG are permanent. They are randomized every 4 rounds. Another difference with the original honeycomb code is that the weight of the stabilizers in terms of checks is actually smaller. We need to take a product of 6 checks in case of the original honeycomb code and only 3 checks to form a Floquet stabilizer in our case. Performance-wise, honeycomb code has been benchmarked thoroughly, and it shows competitive thresholds in comparison to the surface code. But on platforms that have native to qubit measurements, it outperforms surface code, and it also, I forgot, sorry. It also has lower overhead. CSS code has been preliminarily benchmarked, and it has a similar threshold, and it has also been run on IBM Falcon chips, and it has been shown to generate some quantum correlations there, but not really do any quantum computation yet. So now going to the next part of this talk, the codes without periodic structure. To see it, let's assume that the last round of measurements that we did is an RXX round. In this case, the operators of the red type, RYY and RZZ, actually generate electric strings. The X-type operators, GXX and BXX, generate magnetic strings. Therefore, if in the next round we measure either of these, we will collapse the topological code that we have formed by the Floquet code. We can only measure one of the non-commuting types of checks in the next round. This can be nicely viewed from the perspective of anion condensation again. Actually, regardless of which of the anti-commuting types of checks we choose for the next round, the code will conserve logical information, and it also will realize a toric code. Therefore, we have, after every round of measurements, we have a choice what to do next. And therefore, the specific realization of a Floquet code will carve out a branch on a tree of possibilities for the codes. So Floquet codes form the following landscapes. The dynamic codes, not all of them have error correcting properties, and not all of them are periodic. There is an overlapping region. And honeycomb code and CSS honeycomb code are 2 specific examples of good periodic and error correcting codes. In our work, we also show that if we stick to an RGB kind of color sequence, but completely randomize the flavor of each next check, this we call random flavor code. This code will also have a threshold. And if we want to randomize both color and flavor, we can actually design error-correcting codes, which we call probabilistic finite automaton code. This is because we need to store the syndromes that have not yet been updated in the memory, and randomly choose the color and the flavor of next check such that it does not compromise the error correction property of the code. This allows us to generate random codes which are still error correcting, which actually have non-trivial examples that are neither periodic or have any structure on top of them. Now to 3D generalization. To generalize the code to 3D, we start from CSS honeycomb code on a square octagon lattice, and we try to embed it into 3D. We end up with a decorated cubic lattice where each vertex has been replaced with an octahedron. This is almost like a foliation, but not quite, because each vertex of the decorated lattice contains only 1 qubit. Each cross-section of this lattice is a square octagon lattice. So what we're trying to really do, we are trying to put the CSS honeycomb code protocol in 3 dimensions. This actually requires us to modify the protocol. First of all, our red and blue measurements will actually be 3-body. And our color sequence will actually be also modified to RGB BGR. This is to observe the proper commutation relations between these subsequent measurements. And after 4 rounds, this code generates a checkerboard model, which is a type 1 fractal model which has an extensive ground state degeneracy. And it continues to oscillate between different fractal models, which are either X-cube model or checkerboard model. Which also has a subtlety here because, in fact, the ground state degeneracy of these two models is not the same. But nevertheless, we can transport most of the qubits without losing logical information. So the properties of three-dimensional code are similar to those of the two-dimensional code. It can also be made random. And moreover, we find a parent code which is fractal type 1 code, and we can condense linons and planons within this code in order to generate our code. And this is probably not studied fractal version of the color code. Okay, so in summary, we have lifted two structures that could have restricted us from creating new useful Floquet codes, which is the subsystem code and the need for periodicity. We have also proposed several concrete examples of new Floquet codes, such as CSS honeycomb code, 3D fractal Floquet code, and an entire new class of codes which are random dynamic codes, which are not quite Floquet. Finally, I'd like to pose these open questions in this field, which is what is the general theory of Floquet codes and more generally of space-time fault tolerance? How do we classify Floquet codes and associated dynamic phases, maybe, especially from perspective of condensed matter theory? Is there a relation between already existing approaches such as pumping domain walls or condensing anyons? Then there exist other frameworks of computation that seem to be related to Floquet codes, such as measurement-based quantum computation and fusion-based quantum computation. And the question of relation of these frameworks to Floquet codes is not fully explored yet, even though there is already some work in that direction. Then there is always a question of, can we design better Floquet codes or conceptually new, interesting Floquet codes? And finally, how do we do quantum computation with Floquet codes? With this, I'd like to thank you for your attention, and I'd like to thank my collaborators.
Thanks. Yeah, thanks for the talk. So in the middle, I think you mentioned that for this CSS version of the honeycomb code, you only need to multiply 3 of the checks to get the stabilizers. Can you say again, why that is?
Oh, it's because so in CSS honeycomb code, we have X and Z type plaquettes in the ISG. And these are generated just by, in one of the round measurements. For example, BXX generates a green X plaquette in the next round. Whereas in honeycomb code, you would actually always take 2 last rounds of measurements in order to produce something that commutes with green YY in the next measurement. You actually would take BXX and RZZ checks, which together wind around a green plaquette to form green YY check. And that's how you generate the plaquette for the next round. So there is this different way of generating operators that commutes with the next round in the two codes.
But if you just want a stabilizer in that one round, not the the stabilizer that persists through every single round, then you could also just multiply 3, right?
That's true, but yeah, but if you go on with rounds, you'll have to multiply 6 checks in order to do a plaquette. And you care about it because you want to do error correction, and for error correction, you really need to go through more than 1 round, right?
Okay, thanks.
Yeah.
So I've got 2 questions. The first one is there in some sense, what a kind of takeaway message from this is that when we're designing codes, maybe instead of thinking of the stabilizers, we should just think of something that, a set of commuting measurements that all commute with the logical operators?
Yeah, that's way too performance,
And
yeah.
the second one was, have you thought about, for the non-periodic codes, doing adaptive choices? So you said you kind of just randomly choose in
Yeah, that is our
tree.
idea. We think it could be useful for adaptive quantum error correction. If you have biased noise, you can temporarily bias your protocol to take that into account.
Okay, and you could use the syndrome measurements to work out when you should bias.
Yeah, exactly.
Okay, thanks.
Hi, thanks for the talk. So the 3D code,
Sure, you can continue.
yeah. So this one. So if you expand all the octahedrons so that they like touch at the vertices, and you just replace the 2 qubits with 1 qubit, it looks like you get exactly the 3D subsystem toric code.
Yeah.
Is this like, so there's some kind of local unitary almost that maps between these, right? Is this like significant, do you think, or is this just like a weird coincidence?
So I think it's not a coincidence, because in fact, if you insert a 2-body measurement between each 3-body measurements, you actually recover 3D
Okay, I thought so.
toric code. So this code has a 3D subsystem toric code within it, but we just think it's not the interesting direction to use it. Yeah.
But do you think this is a way I can generate more codes which don't have parent subsystem codes, by essentially I take a subsystem code, I kind of replace the physical qubits with like a concatenated 2-qubit code, and I kind of just decouple that code and I recover, because I can achieve this code by doing that to a subsystem code, right?
Yeah, I guess.
Can I do this more generally, or this is a special case for some reason?
I think, generally you can generate any code like this, but then if you continue, so this is approximately what we were doing, but the problem is that once you try to go on cycling through a code and you want it to be error correcting, you want to update your syndromes fast enough in comparison to how you, for example, erase your syndromes. Old syndromes, if that makes sense. So it turns out that meeting that condition is much harder than actually generating the code in the first place. Generating the code once turned out to be the easiest task. Making it like a space-time code in the sense that it can go on in time and still be error correcting, that's the hard part. And we don't have a recipe for that, unfortunately, yet.
Right, it doesn't help to do something like this where it looks almost like it would inherit some of its error correcting properties from the 3D subsystem code, right? Or no, is that not the case?
But I think it will inherit them if it is a 3D subsystem code, but otherwise it won't, right? In a sense.
Right.
Yeah, we can discuss it later.
Okay, sure, thank you.
Yeah, thanks for the nice talk. So I also have a question concerning the 3D code. So you mentioned the parent phase.
Sure.
Shortly. So what does it look like? On which lattice would it live?
So this code has the stabilizers are the product of axis around red cubes. Also, all the qubits belonging to this volume. Then products of these belong to red cube, and similarly products of X and Z around the other cube. And also product of axis and Z's around diamonds that are like diagonal cross sections of the octahedra. So it's like a 3-color. The volumes of this lattice are 3-colorable, actually: red, green, blue.
Thanks.
Thank you for the talk. I have a question about the dynamic tree codes. And then in that size, you have this adaptive measurement of your XX link and then ZZ link. My question is, what if there's an error happening between you measuring the XX link and ZZ link? Would this affect the fault tolerance of this protocol, or if you have some underlying geometric assumption that we're just not aware of?
So that is addressed actually in our construction of finite automaton codes. You really care when you are doing error correction in these codes, because detectors have finite length and time. In fact, you can show that the shortest length of detector that you can have is, I think, 5, which is what we have for periodic Floquet codes like honeycomb code. So because the detectors have finite length and time, you really need the history of what you've been doing in time in order to correct the errors. But as long as what you're doing in time, like is obeying a certain set of rules for constructing or correcting code, you should be able to detect the error. But it really depends on the entire history of what you've been doing. Yeah.
Thank you.
Yeah. Sure.
Anybody? We're back here.
I remember some work on the decoding the fracton, like normal fracton codes in parallel.
Yeah, Martin Delgado. Oh no, it's Ben Brown, I think. Yeah, sure.
Ben is probably on it. Yeah. So did you think about how to decode the X cube or like your fracton code, and can similar
it
techniques
looks like
be applied
minimum
to
weight
this?
perfect matching should be working
yeah.
for it. Yeah, we just haven't addressed this in detail.
Is it always the case that a decoder that works for the code where the ISG is in can be used for decoding?
That's a good question. I think there could be general conditions that we could formulate to say that. That's a good question, actually. Yeah.
Well, I'd still be interested in if speakers come by, we can just have a discussion, 5-10 minutes. But if you're not interested in that, it's okay. As a speaker, you're free to go. But maybe take one more quick question if there is one, and otherwise, let's give a hand for now all of our speakers.